Hello everyone. In this video, I'd like to give you an overview and introduction to hypothesis testing and the intuition behind this. When we learn about inferential statistics, well, inferential statistics is where we are trying to make inferences about a population characteristic based on the sample information that we have. And hypothesis testing is a formal and systematic process in which we conduct statistical inference. Now, what do these terms mean? What is a hypothesis and how do you go about testing a hypothesis? Hypothesis, in simple terms, refers to a guess. So whenever we guess something, so we could guess something about the particular population, and we could term that in statistics parlance, we could say that we are hypothesizing about a particular population characteristic. So what we can do to get started with the process of inference is we can come up with these statements about the population. Remember, we don't know about the population. We're trying to make conclusions about the population based on the sample that we have. But to kickstart that process, we formally state what the conclusion is that we want to draw about the population. And that statement is called the hypothesis. How do we test this hypothesis? We look through our sample data to see if the patterns in the sample match the statement that we are making. If the patterns match this statement, maybe that will suggest that we should maybe consider our hypothesis to be true. If the patterns don't match the statement, then maybe the sample is telling us that the statement that we initially wrote down is not true. In essence, this is what hypothesis testing is about. Formally, we begin the process by writing down two statements. One called the null hypothesis, the other called the alternative hypothesis. So we write down two hypotheses. So the first one is called the null, also referred to as H0. Now, null is usually the status quo. And the null is defined in such a way that we assume the null to be true until we have evidence to prove otherwise. I'll give you an example in just a second. And the other hypothesis we write is called the alternative hypothesis. And it is written as HA or H1, and usually the alternative is the opposite of the null. To give you a simple example, suppose we have a man, Mr. Orange Juice, who is being tried in court for the murder of his ex-wife. Mr. Orange Juice could either be guilty or innocent. We don't know the truth. Now, how will we write down the null and alternative here? A good way is to use the maxim, innocent until proven guilty, to guide our answer. Well, we could consider Mr. O to be innocent. And until we find evidence to suggest otherwise, we're going to conclude that he's innocent and not guilty. Now, the status quo is that we're considering Mr. O to be innocent. And therefore, the null will be that Mr. O is innocent. And the alternative will be the opposite of this, where we say Mr. O is guilty. So essentially, we're defining alternative in such a way that we're going to go and look for evidence to suggest if the alternative is to be believed in and the null is to be considered false. So that will typically be the way in which we approach hypothesis testing. Now, this is a simple example where we're defining null and alternative using simple sentences. But in statistics, we'll generally see problems where the null and alternative are defined in terms of mathematical expressions. To give you an example, suppose you're consuming a packet of chips, and the label on the pack says the pack weighs about 50 grams. But from your experience, you know that it is not 50. So how will you go about checking if your thoughts about your statements or conclusions about the weight, are they true or not? So if you were to test a scenario like that, you will say that you will set up a null hypothesis that the weight is equal to 50 grams. The alternative will be the opposite, that the weight is not 50. So you look for evidence to suggest if the weight is not 50, because that's what you want to prove. So whatever you want to prove will be in the alternative, and the opposite of that will be the null hypothesis. Now, these are the basic starting points of learning about hypothesis testing. Now, how do we actually go about the process? What do I mean by looking for evidence from the sample to know whether it supports your statement or not? Let's take an example. Suppose there are 4 siblings, okay? and we're going to call them A, B, C, and D. And they come up with a very innovative way to figure out who will do the dishes on a particular day. Suppose they all randomly, they decide to write their names on chits and put it in a basket, and they end up picking a chit. And whichever name turns up on the chit, that person needs to do the dishes on a particular day. Now you could imagine variants of this also. Maybe they have a random, the computer will throw out a name that, today B needs to do the dishes or C needs to do the dishes. Essentially, it's a random process which determines who will do the dishes on a day. Suppose we see that for 3 consecutive days, B's name is not picked. Okay. The siblings are all doing the dishes, but for 3 days, this sibling's name doesn't show up. And there are 4 siblings in total. Now, is it reason enough to suspect that there is some cheating going on? That, somebody is tampered with the chits, or maybe somebody is tampered with this computer program, that B's name is not showing up. Maybe D has tampered and cheated. How will you go about testing your suspicion? Well, let's compute the probability of an event like that happening. Now, the likelihood that D's name is not picked on any given day is 3/4. There's a 1 in 4 chance that D's name could be picked if the process were truly random, and if every sibling had an equal chance of being picked. In that case, D being picked has a 1 in 4 chance. So the D not being picked will be the complement of that, and therefore 3/4 is the likelihood. Now, picking chits today and picking chits tomorrow, these are going to be independent events. And therefore, to compute the probability of D's name not being picked for 3 consecutive days, all we have to do is multiply, raise 3/4 to the power 3, and that will give us the probability of an event like that. And turns out the probability of D's name not being picked for 3 consecutive days is 42%. And this is under the assumption that if there were no cheating, if everybody had an equal chance, 1 in 4 chance of being picked, if that were in fact true, the likelihood that we'll see an outcome like this, where D's name is not being chosen for 3 days at a stretch, is 42%. Now, the 42% is not, it's a little less than 50-50. It's a fairly sizable probability. And therefore, it might be fair that, it's not unlikely or unreasonable that an outcome like that is showing up, because it has a 40% chance of occurring. So maybe, it's because the probability is 40%, maybe it would lead you to conclude that there is no cheating going on. This could happen because it's a 40% chance, so I'm going to ignore it. Let's ignore it. Suppose B's name is not picked now for 12 consecutive days. Could we suspect cheating in that case? Now let's compute the probability of an event like that. Well, if everybody had an equal chance of being picked, if there were no cheating happening, then the very likelihood of something like that happening is about 3.17%, which is a pretty small number. It's a little greater than 0. 0 is where it's absolutely unlikely, but 3% is a little greater than that. Now, if there were no cheating happening, there's a very, very small chance for something like that to ever happen. But you're seeing that happening in your life. Now, could that be reason to suspect that somebody is tampered with this process? Maybe there is some cheating going on. Well, because such an unlikely event is showing up, it leads you to think that, I'm really beginning to doubt if there was no cheating. I'm really beginning to think that there could be some cheating going on, because something that is so unlikely is happening. And it begins to cast doubt on the very premise of there being no cheating. Let's consider another scenario. Maybe D's name is not being picked for 15 days at a stretch. Will you begin to have a stronger suspicion? If you actually compute the probability of that happening, if you believe that there was no cheating in the beginning, if you believe that everybody had an equal chance of being picked, then the likelihood of an event like this, of not being picked for 15 consecutive days, is an extremely small likelihood. There's only a 1.34% probability that something like that could ever happen. Now, because it is so rare for an event like this to happen, right? I mean, it is so rare that there's only a 1% chance of it ever happening. You're beginning to wonder if it is that 1% chance playing out, or if it is some underlying cheating happening, which has resulted in a particular outcome like this happening. Now, put this example in the context where I'm defining a null hypothesis that there is no cheating. My null hypothesis here in this scenario is that there is no cheating. And if I were to believe that the null is true, I have witnessed two situations where the probability of something like that is extremely rare. And so I'm beginning to doubt if the null is in fact true. So this is what I mean when I say my sample data is giving me evidence to question if the null is indeed true or not. Now, a low probability value like this, a low probability value associated with an outcome, is suggestive of, it is casting doubt on the null hypothesis. Now, how low must this probability value be for us to conclude that the null is false, that there is cheating happening? How unlike, the event that is happening, how low should the probability of that be for you to conclude that, I doubt if this is truly happening due to chance, I'm beginning to suspect there is cheating? Well, there's no clear or right answer to this. The general convention is that we come up with a probability value of 5%. If a particular event that you're witnessing has a less than 5% chance of ever happening, then because you have mentally set a threshold of 5%, any event that has a likelihood of less than that 5%, you're going to label it as an unlikely event. And when you see such unlikely events, that is suggestive that your null hypothesis is not true, and you have to consider it to be false and therefore reject it. And we'll come back to this threshold in a bit. So generally the convention is to set a 5% threshold. There are some more conservative researchers who set an even lower threshold of 1%, meaning that the event that they're witnessing has to have a probability that is less than 1%, and only then will they label it to be unlikely. And only such unlikely events will lead them to reject the null hypothesis. So this is generally the convention. Now, whenever we end up rejecting the null, we do it because the evidence tells us that the null is false. And the particular threshold value below which we reject the null is called alpha. And we'll see alpha showing up again. So we'll just remember what this threshold refers to is called as alpha. And when we reject the null, we say that we're rejecting it because the probability that we are seeing is not due to chance, but rather there is something else which is happening, which tells me that the null is false. And therefore, this outcome cannot be occurring because of that 1% or 3% chance that we computed. Something else must have changed the underlying mechanics completely. And such a finding, when you reject the null hypothesis, is referred to as a statistically significant finding. And these are all terms that you will hear in a hypothesis test: the null and alternative, a threshold value, a statistically significant finding, and so on.